Uh, Hello all. So this video is the continuation in the second unit. In second unit, we have started the topic of the effect of uh, design and operating variables for SI engine and CI engine. So in that context, we have seen the SI engine design and operating variables. So under that, we have seen a few topics and then discuss. So in this video, we will look at the effect of CI engine design and operating variables. So under this heading, so we have few subtopics to discuss. So if time permits, so we'll see most of the content. If not, we will restrict to the few. The first one is combustion chamber parameters. So under this topic, we have four subtopics. That is combustion chamber type, and then compression ratio. Third one is combustion chamber dead volumes. And fourth one, multi-valve designs and air spill effects. And the second is the fuel injection variables. Third one is operational parameters, EGR, so which we have already uh, discussed in SI engine. And then finally, fuel quality. So we'll see the first type, that is combustion chamber type. Combustion chamber type. In diesel engine, there are two main types of engines, combustion chamber types. So this already we have seen earlier. So if you just recall it, the first type is direct injection. Second one is indirect injection. I hope that so everybody knows that what does mean by direct injection and then what does mean by indirect injections. And nowadays only we can see engines with direct injection type. So, and this IDIs are phased out now. So mostly we don't use the IDA types. So why? Because these are poor fuel economy. So they didn't give much fuel economy. So that's why now these engines are completely eliminated. And how this ID engines are uh, tend to poor fuel economy is, and how this injections or engines are not able to like are not in existence. So we see what are the factors are affecting this IDI. Okay, so if you want to know how actually it is leading to poor fuel economy or in terms of some other emission parameters, we want to look at in the combustion uh, stages of this IDI. So this IDI, so the combustion happens in two stages. Okay. So just we'll see how the combustion happens inside an IDI. So this, just consider this as an inlet. And this is your exhaust or outlet. So this is our pre-combustion chamber. And this is the main combustion chamber. So the injector will not be in main combustion chamber. So it will be in the PCC. So this is our injector. Now when the piston moves from TDC to BDC, that is suction stroke, the air is sucked inside your inlet and it starts moving inside the combustion chamber. Now, once the piston start moving upward, that is from BDC to TDC. So the pressure increases, and then if your pressure increases, again the temperature increases. Now, once the pressure start building upon the air, okay, now the movement of piston is from BDC to DC, the hot compressed air will also go into the pre-combustion chamber. Okay. Now, the amount of air which is going inside this pre-combustion chamber will be minimum. So here we have oxygen will be less compared to the main combustion chamber. Here the oxygen will be more. Now once the piston reaches, once the hot air, compressed air reaches inside the combustion chamber, pre-combustion chamber, now the injector injects the high pressurized fuel, atomized fuel into the combustion chamber. Okay. So this is fuel. Now, since we have all the fuel will be only injected in pre-combustion chamber. Now, here the amount of oxygen is less. Now, all the amount of fuel is injected inside the pre-combustion chamber. The quantity will be higher in PCC. Now, this ratio, oxygen is less, fuel is more. This gives rise to the rich mixture. Okay. Now, the only probability of getting combusted inside the PCC is first the rich mixture. So only the rich mixture alone will be burnt inside your pre-combustion chamber. Right? Now, once the pre-combustion chamber, the fuel gets, the rich fuel mixture gets burnt, the hot fireball, okay, or which will be, we call it as fireball, will be started. So once it generated, it moves to the, in this, that is main combustion chamber. Right? Now, during its flow through this inlet, it creates its own turbulence. Okay. Why? Because we know the characteristics of the fire when it is generated. Okay, it moves in a very higher or faster rate, right? So this turbulence will the moves in very fast rate. Okay, faster rate. Now the moment it goes in the high or the faster rate, the time available for mixing with the air will be less. Okay, so time is not sufficient to get mixed properly. Okay. Now the partially burned rich fuel mixture will be burnt inside the main combustion chamber. Okay, so why? Because here we have more amount of oxygen. So that is one possible way. So the partially burned rich mixture must be get combusted in main combustion chamber. But due to this highly high turbulence, the mixing is not happening properly. Okay, that's why the rich mixture will not get combusted properly in the main combustion chamber, but mostly it will be uh, burnt as a lean mixture. Okay, here in main combustion chamber, it is burning as a lean mixture. So the reason is just now we have so. Now at light loads, if you take at very lower loads, generally we operate at rich mixture, isn't it? So that too, it is happening in pre-combustion chamber. So this mostly light loads, the rich mixture, the PCC contributes more NO. So why? Because the temperature will be much higher in PCC than MCC. So here temperature in PCC is higher. But you take at higher loads, the additional NO formation would occur in the main combustion chamber. So MCC will contribute more NOx at higher loads. Now we'll see the case in direct injection. So in direct injection, so we don't have this kind of setup. So straight away, so the injector is placed inside your combustion chamber. Okay. Now with this setup, we are completely eliminating the turbulence. So the turbulence is completely eliminated here. So when you don't have turbulence, you have much time to mix well the oxygen and the fuel. Okay. So the combustion happens mostly at higher peak pressures and temperatures compared to the indirect injection engines. So that's why if you look at the in the previous classes, if you recall, we have seen the plot for NOx emission for direct injection and indirect injection. So if you just recall that, the plot for which engine the NOx emissions will be higher. Okay. So in this case, again, the IDI will have low NOx emissions when compared to DI is high NOx. So comparatively, because the presence of lower level turbulence during the combustion chamber. Now, if you take, as we discussed in the IDI, the turbulence is not allowing the mixture to get properly oxidized with the oxygen. So if it is not able to get proper oxygen, then again that is leading to formation of or insufficient amount of oxygen, insufficient amount of O2. So when there is insufficient amount of O2, this leads to the formation of carbon monoxide. Okay, so when you have the turbulence, again the formation of carbon monoxide will be higher. Okay. So these are the topics or the concept that which engine uh, emits higher amount of NOx and carbon monoxide based on uh, their design parameters. Sorry, the combustion chamber type. Okay. The second topic is compression ratio. Okay. So we know the definition of compression ratio. That is total volume to the clearance volume. So, and we know the importance of compression ratio for diesel engines, particularly heavy duty vehicles. And already we have seen the importance of compression ratio in our earlier classes. If we look at the naturally aspirated direct injection engines, the CR would be around 16:1. And if you take the turbocharged engines, it is about 13:1 to 14:1. Why? Because the uh, compression of air will take care by your turbocharger. So automatically the compression ratio will be decreased. You no need to maintain that high compression ratio. So now how this compression ratio has an effect on emission characteristics in diesel engine. That is the main focus and objective. Uh, if you just look at an increase in compression ratio, an increase in compression ratio results in shorter ignition delay, results in shorter ignition delay. Now, what happens if your ignition delay is shorter? Means the time which you're giving for the ignition delay, you're just reducing that. So this shorter delay period would result in less over mixing of fuel. Less over mixing of fuel. So already we have seen in the diesel engine what is meant by under mixing and over mixing. So if the mixing happen beyond a proper mixer, that is beyond the stoichiometric ratio. So if you're having, if you give much, they create the uh, like perfect air spill around the fuel, so you can get the proper over mixing. Okay. So this, if you have less over mixing, this will tend to lower the HC emissions. Lower the HC emissions. Okay. So this process takes place if your compression ratio is increased. Now, if your compression ratio is again increased, what happens? This will also leads to the increase in pressure. Increase in pressure leads to increase in higher temperature. Okay. So this high temperature will increase the oxidation of hydrocarbons or UBHC. So once if your oxidation of hydrocarbon increase, so automatically we have the HC emissions will be get lower. Okay, so that's the concept behind in lowering the hydrocarbon emissions. Now, what happens if the delay period is longer? So here we have seen the shorter ignition delay. Now, what happens if the longer delay period? When you have a longer delay period increases, so the fraction of fuel burnt during the pre-mixed phase. Okay, so pre-mixed phase results in higher pre-pressures. So higher peak pressures. And higher peak pressure results in increase in temperature. Now, when you have an increment in temperature, so we know there is decrement in lower. So this will lead to increase in NOx emissions. Okay. But how long this longer delay period is acceptable? So that's the question. So if the ignition delay is too long, okay. So for example, if you take the consider this as an IC engine, this is your combustion chamber. So if you're increasing the delay period too long, so the combustion happens only when in the expansion stroke. Okay. When the combustion happens in the expansion stroke, what happens? Your pressure will be dropped, corresponding the temperature will also drop. Okay, so when there is lower in temperature, again the NOx emissions will be reduced. Okay, but the other effect which you get with this is very poor fuel efficiency. Okay. Yeah. So this is how the compression ratio has an effect on the hydrocarbons and then NOx emissions. Okay. Okay. Now we'll see the third type. That is multi-wall designs and air spill effects. Now, how this multi-valve designs in an engine and this air spilling effect has an effect on the emission. Now, today's like if you take any cylinder, the modern cylinder, we have 3 to 4 valves per cylinder. So if I look at from the top view, so we have 2 inlet, 2 exhaust valves. And here is the injector. This configuration is common in nowadays. Now, what is the use of using this multi-valves? The first one is it increases the airflow area. So we have two valves. So from both the valves, we can get the air. And second one is it increases the volumetric efficiency of the engine. And if you have studied what is meant by volumetric efficiency of engine, you might have understood. Now, if you look at in the direct injection diesel engines, okay, so as we have discussed earlier, so this is assume that the cylinder top view. So here we have two inlet valves. This is exhaust valve. And the injector is placed in the center and vertically. Now, what is the advantage of placing the injector center and vertically means it always have the equal distribution of fuel inside the combustion chamber. Okay, now once it distributes equal amount and the availability of air to each spray for mixing also, right? So that's the advantage of having this kind of design. So if you look at the two valve designs in earlier days, if you take this engine type configuration, sometimes uh, your inlet valve could be this side, exhaust valve could be this side, and injector may be placed some other orientation. Okay, so it will not be exactly vertical and central. It will not be central and vertical. So with this orientation, there are a few effects or exists. Okay, so effect of injector inclination has an effect on the particular matter. Okay, we'll see how that is. We have a small plot for this. To take the injector inclination. So the injector inclination from vertical in terms of degrees. Here the particular matter emission in terms of percentage. If you look at a 10-degree deviation, there is increment of particular matter emission. If 15% or 15 degrees incline or deviation, so this is the range. If 20, this 25, this. If you just plot the trend, it goes like this. If it just touches the peaks and the bottom. So this is the range. If you increase a 5-degree, or if the injector is varied 5-degree from its vertical position. Okay. So this is the range of PM can delta PM. If same for 15-degree, so this is delta PM. So likewise, if you have more amount of or more degrees deviated, the more amount of particular matter emission will be increased. So this is due to only the poor fuel distribution in cylinder because of its orientation. Now, this also has an effect on the two valve and four valve for BSFC and particular matter. Okay. So before that, we'll have a small concept for this. If you take a centralized combustion system has lower swirl requirements and thus smaller fraction of fuel is pre-mixed during the delay period. In four-valve engines, symmetric air motion in the piston bowl and equal fuel distribution between different sprays lead to optimal mixture formation and combustion with very low smoke levels. So centralized combustion system thus results in reduced formation of PM and NOx. Centralized combustion system. So this will lead to give lower particulate matter and NOx. So comparatively, the other oriented type fuel injector. Now, if you take the NOx emissions on the x-axis, this is gram per kilowatt hour, means for heavy duty vehicles. Here, brake specific fuel consumption, gram per kilowatt hour, and particulate matter, gram per kilowatt hour. Now, if you take for particulate matter, two valves and then four valve engines. Okay. So this is the trend which is follows. This is for your two valves. And if you take for particulate matter for same four valves, so this is how the trend. Now, comparatively, your four valve have much better for reduction in particulate matter. Same if you take for this brake specific fuel consumption, your two valve will have a sudden drop and then keep on or maintain same. But if you take your four valve engine, it will be mostly of a straight line. This two valve, this is four valve engine. Okay. So this is how your valves, multiple valves and airs will have an effect on the emissions.